Come, Group A, can talk to us.
Hello.
Hello?
Did I share my screen?
Yeah.
Okay. Sorry, let me check if my group members are here. Okay. Hello everyone. We're Group A.
And you're late? Yeah.
Yeah, we're not late. We're Group A. Okay, and this is our overview. We split the task into 4 parts. First part is baseline and regularization, is for Philip. The second one is for Booster. The third one, hierarchical, is for me. And I'm Will. The final part, the calibration, is for my rod. Okay.
Hello?
Hello?
Can you hear me?
Yep.
Okay. So for this project, we use data from NHANES. I'm not sure can call it enhanced, but anyway, the National Health and Nutrition Examination Survey. NHANES is a large ongoing US survey that combines interviews with physical exams. So it provides a wide range of health-related information on the same individuals because it includes the demographics, diet, lab tests, and medical conditions altogether. It is a very strong data set for statistical modeling. And our main outcome is HSD 010, the self-rate health measured. And participants answer one question. In general, would you say your health is excellent, very good, good, fair, or poor? The enhance code these responses as 1 for excellent, 2 for very good, 3 for good, 4 for fair, 5 for poor. So HSD 010 is an ordered categorical variable with 5 levels. So in our analysis, we treat HSD 010 as a multinomial outcome. This means we modeled the probability of each health category instead of collapsing them or forcing the scale to behave like a contingent score. This approach keeps the original structure of the data and allows the model to capture differences across the full range of health ratings.
Very good.
So we started with the unregularized multinomial logic as our performance floor. It models the chance of choosing one category, like excellent versus a reference category. In my case, I chose poor for in every case. And how this exact model works is it doesn't have C penalty. Like it has, but it's very high, like 10 in 8th grade. So you can say that it doesn't have. And the results that we got is the overfitting. You can see it's on baseline train log loss is 1.20 and baseline test is 1.26, which is what we will do better in task 2, right? Next slide, please.
Yeah, so remember here the discussion that we had on the fact that, you cannot convert this course into probabilities so that you could have, so in your case, yeah. Okay, you understand what I'm trying to say, yeah.
Yes. So for task 2, we applied less L1 Lasso, L2 reach, and elastic net penalties. The goal was to tune the strength of the penalty represented by C using the validation set to find the lowest possible log loss. The key difference between the penalties is the effect on the coefficients. Like reach shrinks all coefficients to make the model stable near zero, while Lasso forces weak coefficients to zero to make the model sparse. And elastic net is a combination of both, depends of raw coefficient. So the best results that we got is reach, where log loss was 1.25 in the test. You can see it on the graph. And next slide, please.
Can you also, yeah. So here you chose the lambda that gives you the best log loss, right? Correct?
Yes. Here is the most important feature of Lasso is feature importance graph. We can see the first two position, which what I find interesting is binary ones. The most important one is one if person has a college degree. So it has the most influence on people's health from our model. And second one is one if person is Mexican American. Third one is continuous. It's body mass index. So the higher it is, the more obese person is. And
I mean, let me rant a little bit because last time, we were discussing the BMI, and I posted an article about the BMI, right? Because the students were shaming me because my BMI says obese, and I was arguing. I'm actually an athlete, right? So my body is all made out of muscles and steel. That's why my BMI is so high. But yeah, I mean, so there is a quote in the article that says that the BMI is wonderful on a population level, but it's terrible on a personal level. And I think there is something true about it, right? Because the measure is very simple.
yes.
Doesn't tell you about the body composition, but yeah, it's.
And also very interesting thing is the least popular ones. The least popular one is also continuous, and the higher value it has, the more like bad cholesterol person has in its blood, in their blood. And second least popular is also binary, and it means one if no running, swimming, or any activities that increase heart rate. So yeah, that's interesting.
Yeah, so this is important because so you see that okay, just as I'm not a doctor, right? There's a discussion. So the point is that these are self-reported health, right? So
yes,
it's saying something also about people's attitude. So the LDL, this cholesterol is sort of a classic, right? Because people say that this is the silent killer, right? Meaning that you can have high cholesterol, and you don't feel anything about it, right? So yeah, it makes sense. And if you are inactive, that's not important to be happy. I don't know. I mean, I guess it depends on the sport and stuff. But yeah, most of the Mexican American is interesting.
yeah. And next slide, please. The last graph I want to show you is Lasso coefficients heat map, top 15 features versus reference class. It actually means, for example, for first most popular feature, that like minus 0.6 means that there is less chance that people with this feature will choose 4 over 5. So like, and yes, the interesting thing is that college degree is still like the strongest one. Yes, it's the only one that has 0.63, so the strongest value at all. And also BMI is the one with the least popular, the least probability of going to the very healthy. Yes. That's all for me. Thank you.
Okay. And for Booster is currently hiking, so he recorded a video a few days ago. So I'm gonna play the video. Do you guys hear the sound or not?
No, we don't hear any sound, but you didn't class.
Um.
You have to share a tab and share the
Okay,
audio
okay.
with you. Yeah. And it has to be a Chrome browser.
About ordinal outcomes.
Do you guys hear anything? Okay.
I mean, should we ask the people, because there's some foreigners in the class? Should we ask the foreigners if they know what mountain is this? Yeah. He really went there. He really went there.
Yeah, I think. But I'm Taiwanese. I don't know what mountain.
I'm gonna
it is.
slap you. You come to my office, I give you a slap, and you walk away. You don't know which mountain is this.
Let me take a guess. It's a Mount J.
You come to my office, I'll tell you if it's right or not. You come to my office. You come to my office. Anybody else know which mountain is this?
Hehuanshan. Okay. I'm saying every mountain I know in Taiwan. Yangming Mountain.
Yangming. Tell me the names. Then there is
Ali. Okay, Alishan. Alishan. Okay.
Yueshan.
How do you tell this is Alishan?
No, this is not Alishan. This is not Alishan.
No. So, okay.
But come to my office. We'll discuss. Yeah.
Thank you. No, thank you.
Hello, I am currently walking down a mountain and I cannot be here to present. Therefore, I have made a video about ordinal outcome labels and the ordinal logistics model. Now, you would hopefully already have heard about the multinomial logic model, which which does not assume that you have an ordered data set. But in this particular case, where our data is like this, where you go, I am healthy, strongly disagree, agree, strongly agree, where there's a clearly better option and a clearly worse option, i.e. strongly agree and strongly disagree. We can order them, and we can take advantage of that by, instead of predicting, is this equal to, is this value equal the same as strongly disagree, we can say, is this value strongly disagree or below, or strongly agree. And that's what this model tries to do. So starting off, we will use the same predictors as we used in the multinomial logic model, but we will see that we will have to cut some of these off, because in this model we assume that the predictors that we use have a similar effect across cumulative splits, which means that the coefficients, this eta here, has to be the same as we go up in this J value. Yes. So we do the model on the first, on the big list of predictors. We get a confusion matrix that's consolidated more towards the middle, but that's because much of the data, most people are ordinarily healthy. They're not. So that is what you would see. There's not that many people in the data set, about 9 people, that are actually about 9%, not 9 people, that are actually have reported a value of 1 in this data set. We get comparable accuracies and comparable log loss as the multinomial logic model, but we had an assumption. How is that doing? Well, if you look at this, but there's clearly a lot of predictors here that don't change much in their coefficients, as the color, the heat map is mostly the same here, while there are some, like this PAQ 650, which changes a lot. So we have to remove this, because our model assumes that this does not change. In this model, I have just made an arbitrary cutoff of 0.15 coefficient C change or coefficient C range, so 0.075 in the difference. But we will remove most of these. And when we do that, we find that the confusion matrix is mostly the same, although we do see that we consolidate more predictors towards the middle. So we are predicting the number 3 more. This might be due to the fact that the predictors that did not have an equal effect on all our splits, they might be more. They might be able to drag the corners, so like 1 and 5. They might be able to drag more predictions towards those, and it makes more sense that these are the more volatile ones, because being super healthy and being super unhealthy would have the more volatile effects. But the interesting thing about this model is that our accuracy degrades, but it's really not that much. The same with the log loss. So we can cut off, I don't know, I think it was about, in this one, I think it was about 13 parameters and still get the same accuracy results. That's pretty good. But are there now any in our models that needs to be cut off? Yes, there is. I mean, you can specifically see on this RxD count that it has a heavy weight upon predicting number 1 compared to or because this is positive, this would mean that it has a heavy weight towards not predicting number 1 because of the way the model works. So if it's positive, it means that it wants to predict up, and if it's negative, it wants to predict down. Same with this one over here. But when we do this, we see mostly the same trend. We are narrowing our confusion matrix a bit more. But again, we are also degrading our accuracy a little bit more, but it is still comparable to what we had before. So it's still pretty nice. And we are down to 11 parameters, I believe, which is a huge cutoff from 26, which is what we started with. And our assumption is now doing fine, as it, even though the heat map, of course, now is changed because it's not the same range that it covers. My arbitrary cutoff of 0.15 is now mostly held. What I do find interesting is that you see that all of these values over here, they have a tendency to vary quite a bit more. And then when you go up the threshold, they start to approach 0 mostly. Some outliers, of course, specifically BMI up here. And I try to reason why this might be, why all of the predictors tend to either favor predicting 1 or not, or the opposite in a strong fashion, which is what you can see here in this, what I would call variance in the coefficients. They're not approaching a single value. And I came down to the fact that if I was feeling quite bad and I typed in 1, that would be probably a pretty clear reason for it. While if I didn't type 1, there would also probably be some other clear reasons for why I wasn't feeling completely bad. While the other ones I believe to be a little bit more muddy. Defining whether or not you feel extremely healthy or if you just feel healthy is a little bit more personal, but I'd say that feeling strongly unhealthy, or whatever the survey asks you, there's usually a pretty good reason that you know of as a person who answers that, and therefore you probably see a lot more strong coefficients when predicting 1 compared to predicting any of the other thresholds. Yeah. I think that was about what I had to say about it. Of course, I can't answer questions, so boo-hoo. But yeah, over to the hierarchical multinomial model, which will hopefully improve the fact that that we are not predicting 1 or 4 or 5 in this model.
Okay.
We'll ask him next week, right? We'll ask him next week when he shows up with a nice tan and very relaxed, and yeah.
Yeah, and if you notice, he's using PowerPoint, so he got some powerful points. Okay. Now I'll talk about the text for the hierarchical multinomial logic, and I'll start from something more familiar, the booster, saying the ordinary multinomial logic, which is so-called a pooled model. And in the standard multinomial logic, for each health level k, for example, k is equal to 1 or 2 or 3 or 5, for our HSD 010, we write an equation like this. And the baseline is just one health level we choose as a reference class. And in this equation, the beta 0k is the intercept for class k, and beta k is a coefficient vector for the predictors in class k. And everyone shares the same set of betas. Okay, in other words, the pool model, we're assuming that age doesn't matter, and the effect of BMI, blood pressure, income, and so on the log odds is exactly the same for young people and older people. But in our data, observations are not completely independent. People are naturally grouped by age. So we split the age into 3 groups. The first group is 20 to 39. The other is 40 to 59 and 60 plus. So people inside the same age group may share similar lifestyle, like maybe disease burden, even similar feeling about their health. So if we keep using a pooled model, we completely ignore the within group similarity. So in this text, we use a hierarchical multinomial logic. Intuitively, it is a usual multinomial logic plus 1 extra level for group-specific random effect. So for example, for the intercept of class K, we allow each age group to have its own shift, like this. And here the G is a group index in our case, the age group. And the beta 0k is the overall mean intercept for class K. And U0kg is a extra deviation for the age group G in that class. And there's nice thing about this is that different age group can have different health distribution, but we don't completely separate a group. Like the random effect are partially pulled towards the overall mean. That means small group won't get extremely noisy or crazy estimated. And we applied a multinomial logic to our outcome. And the outcome is HSD 010 from 1 to 5, roughly the excellent to poor. So the grouping variable is a age group with 3 groups, like I said. And our goal is to compare the poor multinomial logic and the hierarchical multinomial logic. So first, we can look at this stack bar plot. It shows that within each age group, the proportion of people in each HSD 010 level. So we can see for the youngest group, the 20 to 39, most people in HSD 010 is equal to 2 or 3. That means very good or good. The fair and the poor category are relatively rare. And for the 40 to 59, the bars for 3 and 4 becomes higher. That means people shift towards the middle or worse health categories. For the 60 plus, the bars for 4 and 5 are clearly larger. So that means more people rate their health as fair or poor. So this plot already tells us age has a strong effect on self-rated health, which is exactly why a hierarchical model that respect the age group structure makes sense. And next, we will see the overall predictive performance. The left panel shows the accuracy. The right panel shows the log loss. In the accuracy plot, we see the pool model on training data has accuracy around 0.45. The hierarchical model has very, very small, very similar accuracy. And on the independent test set, the pool model still has accuracy around 0.44. And in the log loss plot, all the 3 bars are also very close, around 1.2. So in terms of the average performance, the hierarchical model does not magically give much higher accuracy. So both models perform quite similarly, which is reasonable because they use a same covariate. And the hierarchical structure mainly adjusts a group level effect and the uncertainty rather than just simply boosting the accuracy number. And accuracy alone is a bit boring, so I look the confusion matrices on the test set. The left one is a pooled model. The right one is a hierarchical model. The x-axis is a predicted HSD 010. The y-axis is a true HSD 010. So the brighter color means more people in that cell. Starting from the pool model on the left, most predictors fall into the level 2 and 3 and 4. The model almost never predict 1 or 5. That means the model tends to play safe and push people into the middle categories, and it's quite conservative about saying someone is excellent or poor. And if we look at a hierarchical matrix on the right, the overall pattern is very similar, especially for the true level 3. And both models predict 3 very often. But in some cells, the hierarchical model has slightly brighter colors, which suggests it's a little bit more accurate for certain edge groups. So in short, the hierarchical model does not change the global error pattern, but it somehow fine-tunes the prediction for specific groups.
The group 3 was where there was an improvement. Go ahead.
Yeah, and on this slide, we look at 2 things. The model confidence and performance by the age group. On the left, we had 2 histograms. The top one is for the pooled model. And for each person we take the maximum predicted probability among the 5 health levels. And the bottom one is just do the same thing for the hierarchical model. Both histograms are concentrated around 0.35 to 0.5. That means even for the best guess, the model is not super confident. It often says something like, I give this class 40% probability, and other classes together still have 60%. And the hierarchical distribution is shifted a little bit to the right, which means after including age group, for some people, the model becomes a bit confident. And on the right, we show the test accuracy by age group for the pooled model. The two younger group, 20 to 39 and the 40 to 59, have similar accuracy, and the 60 plus group has slightly lower accuracy, which might because older people have more complicated health condition, and our simple covariate like BMI and some incomes are not enough to perfectly separate all 5 health levels. And next, we're gonna highlight 2 important covariates. And the first one is BMI. On the left, we have the box plot of BMI for each HSD 010 level. There's a very clear trend from HSD 0.010, 1 to 5. The median of BMI increases, and the spread also becomes larger. So people who feel their health is worse tend to have higher BMI. And on the right, we show from the pool model, the predicted probability of the pool health as a function of BMI with separate curve for the 3 age group. And the x-axis is a BMI, the y-axis is a predicted probability. All 3 curves are increasing as BMI goes from 20 to 40. The predicted probability of poor health grows from around I see 1 to 2% up to 5 to 6%. At the same BMI, the older people groups have slightly higher probability, which is consistent with what we saw before.
But here
yeah,
the 50 and the 60, they are switched, right? You would expect that it keeps increasing with age, right? Maybe.
Yeah, maybe. Yeah. And putting these 2 plots together, we got a very intuitive message. It's that higher BMI is associated with worse self-rated health. And this pattern appears across all age groups. But for some athlete, like professor, this may be not suit for you. Okay. And finally, we look at income measured by the INDFMPIR, the income to poverty ratio. And in this figure, we plot 2 curves from the pooled model. The blue curve is the probability of rating health as excellent. The orange curve is the probability of rating health as poor. The x-axis is income to poverty ratio. So we can see that the blue line goes up, means higher income is associated with a higher chance of reporting excellent health. And the orange line goes down. That means higher income is associated with lower chance of reporting poor health. So in our multinomial logic model, BMI and income play somewhat opposite role, as higher BMI pushes people towards worse health categories, but higher incomes is protective factors, pushing people towards excellent or very good health. And the reason I want to do income is because there's one funny thing we can see from this plot. And this pattern clearly tells us this study was not done in Taiwan. Why is that? Because in Taiwan, people with higher income are usually doctors or engineers, and these jobs in Taiwan are extremely overworked, like TSMC. They got literally no work-life balance, and people like to joke that they basically just earning money for the future medical bill. So I want to see that its income is good for your health or not, because in Taiwan it seems like it's not, but in this plot it is. So this plot is not this study, I think, is not done in Taiwan. Okay, and that's my part. And there's a quick wrap-up is we use hierarchical multinomial logic to incorporate the age group structure. So overall predictive performance is similar to the pooled model, but the hierarchical model reveals how each age group differs in their health level. And it confirms that the expected relationship between self-rated health and BMI and incomes.
Very good, very good. Very good.
Okay.
Am I right?
Now I'm going to talk about calibrations. Classification models outputs like not only predicts class but also a probability. So like if the model predicts like 0.8 confidence, it should be correct about 80% of the time. But however, many models are overconfident or underconfident. So meaning that their predicted probabilities does not match reality. And this is a problematic in real world applications such as like medicines and policy making. So therefore, probability calibrations is important to ensure that the model's confidence reflects the true accuracy.
So here the
Yeah,
G, yeah. Oh, go ahead. I just want to, if you can tell me what type of G you consider in the rest of the presentation, that'll be great. But go ahead.
The first method is temperature scaling. Suppose the model outputs logit Z. The original softmax probabilities are like the first one, and the temperature scaling introduces a single positive parameter T and rescales the logits to the second formula. So now if T is over 1, then the distribution becomes softer and less confidence. And if T is less than 1, the distribution may become sharper and more confidence. So in my code implementation, I estimate T using the validation test, but it's a set, and the model weights are fixed, only the scalar T is optimized. So the optimization object is validation log loss. And the fitted T is then applied to the test logits to obtain calibrated probabilities. Then here's this isotonic regression, which is a non-parametric monotonic calibration method. So it learns a function g of c that maps the model's original confidence scores into calibrated scores. So the key constraint is that this function must be non-decreasing, meaning higher confidence should never produce a lower calibrated probability. Like this formula, like if g of c is less than or equal to g of c2, then c of 1 must be less or equal to c of 2. So in my task 6 implementation, I applied isotonic regression to the top 1 confidence. Of each model, we then rescale and we normalize the full probability vector so that the reported probabilities more faithfully reflected the true correctness frequencies. Yep, next slides. So in my task, I performed calibrations such as this two. But however, I found some problems while doing the hierarchical multinomial logics. First, I found that the hierarchical model does not produce logits. The temperature scaling relies on raw logits before the softmax, but the PYMC only outputs posterior probabilities. So without logits, the method is mathematically impossible to apply. So, and second, the hierarchical model is Bayesian, meaning it generates a distribution of predictions rather than a single deterministic probability for each sample. So calibration methods require exactly one probability vector per data point. So posterior samples cannot be directly calibrated. So I've encountered many problems while doing this task force. So
don't say problems, say challenges. Say learning opportunities. Okay.
yeah, learning opportunities. Yeah. Excites. So here are the ECE and MCE. So this table compares the accuracy log loss and the expected calibration error and the maximum calibration errors before and after calibrations. So we can see that accuracy does not change after calibrations expected because calibration adjusts probability estimates, not class predictions. And log loss, ECE and MC reflects how well the prediction probabilities align with reality. So you can see, yeah, for the L1 regularized multinomial, the temperature scaling slightly improves the log loss and ECE. However, the MC has a slightly upwards because of the low sample counts in some bins. So maybe, yeah. And then
That's what
task
you said
2,
last time, right? You have like 10 samples, so how can you calibrate? Go ahead.
and task 2, like temperature scaling improves every metric, showing better calibrations. While in task 3, isotonic slippage can be worse than log loss. And model confidence is highly concentrated, so calibration is maybe ineffective. So I think that this test does not benefit from calibrations, but I'll talk about it maybe later. So in ordinal logistic regression, the class probabilities are derived from cumulative logics. So when applying isotonic regression, independently to each class probabilities, maybe the adjusted curves may violate the original ordering or cumulative structure. So as a result, the final arguments of the maxima may change for some samples, which slightly alters the accuracy. Next slide. So here, the slide shows the calibration results for the L1 regularized multinomial logics. So the blue curve is the original model, and the orange curve is the after temperature scaling with T approximately about 0.97. So you can see at the numbers, the accuracy is about 0.447, and which is roughly 45% of the test predictions are correct. And you can see that from the plots on the right, you can see that in the bins, you can see that in the 6 bin and the 7 bin, they only have one example count. This is why that the blue line has a accuracy of 1 and 0, because there are less samples counts. Next slide. So now we look at the task 2, the polled multinomial logic model. So since this model does not use L1 sparsity, it behaves more smoothly than the first one. So again, the blue curve is the original model, and the orange shows the results after temperature scaling with T approximately 1.06. So you can see that accuracy is about 0.45, and log loss is around 1.268. And you can see that in the middle confidence range, 0.4 to 0.6, both curves lines close to the diagonal, meaning that the model's confidence is quite consistent with the accuracy there. But you can see that at higher confidence, like 0.6 to 7, the blue curve clearly lies below the diagonal, so indicating overconfidence. So the model predicts around like 0.65, but the actual accuracy is only about 0.3 to 0.4. So after temperature scaling, you can see the logics are flattened, pulling down the highest probabilities, which is a better thing to see. Okay, next. Finally, you have the task, the ordinal logic model. So this model treats the health status as an ordered categorized variable from 1 to 5, and its structure naturally avoids extreme sharp probabilities distributions. So you can see that it only has 2 kind of sample counts in 0.3 to 0.4 and 0.4 to 0.5, and the other all is like 0. So unlike the former, the 1 and 2s, which make several bins, this model produces only about 2 points. This means that almost all top 1 confidence fall within a very narrow range, roughly just above 0.4. So the model is therefore very conservative. It almost never predicts 0.7 or 0.8 confidence. Yep. Next.
Very good.
So this is my part.
Okay.
Very nice. Very nice. Good job, guys. Yeah, it was nice. It was nice. Yeah, very good. Very good. Yeah, very nice. Well, of course, the presentations are always great for this group. Right? You guys are the best. Almost cheating, you know. You have extra capabilities in your slide making. Very good. So I think now is Group D is also here, right? Group D is also you also to present today, correct? Group D. Group D is Group D here? Is there anybody from Group D, guys?
Group D here.
Didn't you have to present this week, Group D?
Yeah, so our group was supposed to present this week. However, we have recently encountered some issues that two of our group members have to go for the
You told me.
military checkup. Yep.
Very good, very good, very good. Okay,
Checkup
so
and there's the other one who is pretty. Well, I think she caught a cold and can barely speak with any voice at all. So this means that we have only two of our group members available today, and I don't think we can present well with only two people here.
very good. Okay, no problem, no problem. Okay, so let's go around the other groups just to see if you read the challenge, how is it going, if you plan to change the team or if everything is okay. And then we cover some new material. Okay, guys? So Group B is Group B here? Is Group B here?
B? Group B?
B like banana.
Oh, yeah, here.
So did you read the new challenge? Do you have any questions? How is the group going? How do you plan? Is the same group as last time? Just tell me a little bit. Yeah.
Same group as last time, and we distribute the challenge into 5 parts. So everyone get their part. Yeah, and everyone is working on it on our collab. Yeah.
Okay, you
We
use
just
Colab,
open a
okay.
collab.
Very good. Do you like the challenge? Is that you think it's interesting?
Yeah.
Very good. Very good. Any other comment?
No.
Very good. Very good. Very good. Okay, Group D is there. We heard from Group D already. Is Group E here? Also known as my favorite group. Is Group D? Somebody here from Group D? I guess they're not my favorite group anymore. Is Group D here? Group D. Sorry, Group E. Group E. Is Group E here?
Yes, but I'm in the library, so I can't really much talk at the moment.
Just tell me, did you split the job? Are you going to stay the same? That's it. 3 words. Just give me 3 words.
We are keeping the same, and we have split the jobs.
Okay. Okay, very good. Okay, so let's move then to the material for this week. Let's have a small break, guys, so that we can go walk around Ring War MP, and then we start with the new material. Okay, guys. We can also discuss the final challenge. So if you want to discuss the final challenge, let me know, and I'll discuss it with you briefly. Okay. Give you 5 minutes, 4 minutes break. I'll see you back at 20. Okay, guys. Go drink some water. Okay, guys, so let's do a little bit of frontal teaching. So I'll just remind you a little bit where we were last time, and then try to move forward. Of course, if you have any questions, let me know. Tell me if you want to talk about the final challenge, or if you want to wait to do it some other time, right? Let me ask in chat. Do you want to discuss final challenge? Question mark 0/1. View full screen mode. No comment. No comment. Okay, so now we share this the window. So I'll just remind you of the what we're doing last time, and then we move forward, right? Because yeah, we try to minimize the frontal teachings, which means that sometimes we had a couple of weeks between lessons on frontal teaching. So remember that we were doing decision trees, right? And then we said, well, decision trees are good, and they're also cheap, so we can have multiple decision trees. And then we said, well, if we do decision trees, then we end up with a very good interpretability, but the power is sometimes small, right? Because very few parameters, so we would like to improve the power so we can have multiple of them. And then we said, well, if we have multiple of them, we can try to use some cross-validation, but then they end up being too correlated. So something that we can do is to do some random forest, right? And the idea is that you want to decorrelate the multiple trees that you have in an ensemble of trees in order to have more power, right? We to have more power in your test. And we said, well, how can we decorrelate them, right? And the idea is that you choose the feature over which to split in the decision trees randomly at each step, and then you find the best predictor for this random variable, and then you repeat. You obtain multiple trees, and once you obtain multiple trees, then you treat them as a pool of experts, basically, right? And we said that this is very nice. We like it. We can have very complex decision boundaries if we do this, and also we have some very good. We retain some sort of interpretability because we can see. So we can see what are the features that are in the trees which determine the splitting. Okay, so once we do this, everything is being sort of understood, because now the splitting, we don't need to have a criterion for the splitting. We can use random splitting of the variables. The idea is that we still have to decide how many random predictors to use at each split. Of course, we can have a single one, we can have multiple one, and have some sort of decision boundary between the split, the total number of trees in the example, and then remember that we have the splitting criteria, right? So we have to decide whether to split a node at a certain point of the algorithm, and so we have a maximum depth size so that we know how deep is the number of leaves that we can have. Of course, in theory, right, we could fix the maximum depth and have all the trees having the same depth, but this is computationally expensive, and sometimes it doesn't buy you much, right? So sometimes you arrive in a node, and the purity of the node is very large, so you don't need to split further. So it makes sense to have a variable depth of tree length. So as we said, when you have a hyperparameters, you can of course do some cross-validation in order to choose the optimal parameter. You can have a validation set aside, but sometimes you just want to have some rule of thumbs that you can use to operate. And usually people have these numbers in mind. Remember that we discussed this already, right? So I'm going a little bit fast because we are reviewing this. So you split the square root of n feature for split when you're doing classification, n over 3 for regression. Remember that we can use the decision trees for both classification and regression. For classification, we just assign one class to each leaf, and for regression, we can have either a linear model when you arrive here, or have some other type of weighting of the different trees. And in this case, is n over 3. Very good. Then we can still retain some variable importance. So we can see a mean decrease of impurity for each node. And so we can retrieve from this the importance of a certain set of features. And then you can also record the prediction accuracy for the out-of-bag samples for each tree. And then you calculate the total amount of RSS, of Gini index, which is resulting from the splitting of a certain variable. And in general, you're going to see a decrease in accuracy of the tree ensemble because you're randomly splitting them. So some trees are really bad, but you gain in expressive power, and you can retrieve the variable importance with the usual trees. So there are some also new measures of importance that arise from the fact that you're working with randomly selected features. One is this permutation importance. So what you do is as follows: you record the prediction accuracy of the OOB samples for a certain tree. Then you randomly permute the data for column J in the OOB samples and record the accuracy again. And then the decrease in accuracy as a result of the permutation is averaged across all possible trees. And this is used as a measure of importance of the variable J in the random forest. Okay, and then of course you can have more complex variables that that are being studied consistently in the literature. Okay, so of course there is always more complex approaches that we don't discuss in class because we are not doing research, we are doing teaching, and this is a laboratory. Okay, so remember that this was again health prediction, maybe something like that. But basically, yeah. So you recover this type of graph of the feature importance. Okay, and for example, the group that presented before, they also had this type of pictures on the variable importance. And then, yeah, so we can compare the variable importance across different models. In this case, we have random forest versus bagging. Some final thoughts, which is when the number of predictors is large, but the number of relevant predictors is small, then the random forest can perform poorly. Makes sense, right? So we saw again with the last example that sometimes you have to remove predictors that are just introducing noise in the model in order to avoid these features ending up somewhere high in the tree, so that the tree has a very poor prediction. It's not a very useful tree. And then if he ends up in the embedding, it's fine. But if you have multiple very weak trees in the embedding, then this decreases the performance of the ensemble. I think this makes a lot of sense. The nice thing about random forest is that you can really have a very large pool of experts, right? So increasing the number of trees generally does not increase overfitting. And this is again because these trees are independent. So the law of large numbers, right? The averaging is not affected by adding a large number of trees. Well, what you can do is that you can again, to show this, you can again consider the splitting of the generalization error in terms of bias and variance. And you see that if you increase the number of trees in the model, there is the result in the model which is as robust as the single tree. However, if the number of trees is too large, then the ensemble may become more correlated and increase the variance. Because of course, if you have many trees, so that the number of permutation is so large that you recover correlated trees, then the correlation between the trees will again come back and bite you. Okay. Again, the issue of calibration. So we can use random forest classifiers to return the probabilities. And yeah. And these are the next features in the next topics that we're going to see. Okay, good. So this was a little bit reminder there. And then we do gradient boosting. Okay. Let's, are we in full screen? Not yet. We want to go full screen. Full screen mode. As always, we thank our friends at Harvard for sharing the slides. So what are the questions that we want to answer today? When I do boosting, can this result in probably in overfitting and underfitting? How should we choose the boosting over the random forest? You saw before that both methods they both are able to produce probabilities, so they are comparable in their performance. Yeah. How does the random forest deal with imbalanced data? When should we boost over random forest? So these are the questions that we want to do. So we want to do a model comparison. So here we have all the models that we have seen so far in class. So we have linear regression, polynomial regression, regression trees, Bayesian and random forest, and k-nearest neighbor. You can see a little bit of a comparison of this model now. So which ones are parametric, which ones are non-parametric? Linear regression, polynomial regression are parametric. Whether the regression tree is Bayesian and k-nearest neighbor, they are non-parametric. Okay. Remember? So k-nearest neighbor was the only non-parametric method that we saw after sort of the first class, right? Then we had this long dive into parametric methods. Then are they easy to interpret? Linear regression, we say yes, right? Because for linear regression, we have a lot of basically each parameter will tell you, will have an interpretation in terms of importance of the feature. Polynomial regression, we said no, because we can increase the number of terms that we have in our model, and we lose the interpretability, because let's say that we have the same parameter that appears at multiple powers, right? How can we say that the multiplication of the height times the weight to the power of 3 being associated with a parameter of 0.37, whether this corresponds to a large importance of the weight parameters, right? It's not so clear. Regression tree, we said yes, because we go down the tree. Over each tree, we see which parameter we're splitting. We come to a decision. So in a sense, we can trace back what is the rule that we use for deciding a certain label for an input sample. Bayesian and random forest. So here it's yes and no, meaning that we have a large ensemble. So we cannot go and inspect the forest and see how many trees in the forest contributed to a certain decision. So this decision in the single tree is still interpretable, but when you have multiple of them, then very hard to look at 100 trees and find a pattern there. But they remain interpretable in the sense that we can still do feature importance, right? You can see how a certain feature across the random forest or across the bags that we have has contributed to a decision for a certain data point. And then k-nearest neighbors, we said yes, because basically these are local decisions, right? So when you're given an input sample, you see the samples that are sufficiently similar to this sample, and we take a decision based on this. So you can directly understand which sample in the data set provided an indication about the current sample. And then computational complexity, of course. So for these regression methods, it's very simple. It's just generalized inverse multiplication, basically. For regression trees, it's also very simple. You can imagine that you just have a set of indicator functions, right? You just have an if-else, set of if-else, cascaded if-else, right? So very easy. Bayesian and RF, this is something we can discuss, because of course the single tree, again, it's just an if-else loop. But then if you have hundreds of thousands of them, then it becomes high. And for sure, what is a very high complexity is is k nearest neighbor, right? And here the complexity is maybe how can we say this? This is both a computational and a memory complexity, but it's you can trade off between these two complexities, meaning that you can have a pure memory complexity, meaning that you keep the whole data set, and when a sample comes in, then you just travel throughout this list to find the closest neighbors. So this is a nearest neighborhood search, which you guys understand can be sped up with some specific memory technology, like storage technology, but in general, the complexity of search over a large data set doesn't scale very nicely with the size of the data set. Or what you can do is that you can use some computational methods where you describe the boundary for a certain set of input features through some lower dimensional predictions. Let's say you can find some sort of separating hyperplanes that you can use to figure out the closest sample to your current sample. And in that case, you're trading off memory complexity with computational complexity. But basically, k-nearest neighbor is dumb because it goes back to the original data set when we have to do inference, and this is a large object that has to be managed in some way, over which we have to do a search operation, which is not a simple operation in general. Good. And okay, so now we come to the following question. Can a set of weak learners create a single strong learners? And the example that we're going to look here is how many jelly beans do you see? Right, meaning that you can have many simple predictors of how many jelly beans are here. And then if you take the pool of this, then you're going to get a strong predictor. This is the classical example of what is called the wisdom of the crowds. Okay, so there was this, I think they were doing with the weight of cows or something like that. There was this statistician that was going to cow option, from cow option to cow option, if I remember the story correctly. Okay, I'm not a historian of statistics. So, and basically, what he noted is that people will have different guesses about the weight of cows, and each of them was generally out of range. But if he had to average across the crowd, right, then the crowd will be right in general. And the example with the jelly beans is that because I think there were a few television shows or whatever, few instances in which people were guessing the number of beans in the jar, and then of course each of them is off. But then if you take the average of all the guessing, then generally that gets closer to the true value. And again, the idea is that if you each of the person guessing, it's a weak predictor, meaning that of course they're just relying on their eyes to count this, right? So they cannot have a very good prediction. But if you had to average all of them, then the prediction will be very accurate. Okay, very good. Okay, so this is a nice meme. This is more of a cookie meme. You can go home to your wife and try to teach your mom how to cut onions. Maybe your grandma, so that you also get cut. You get mom crazy. So you can check the slides, and it's telling you what is the optimal way of cutting an onion, so that the onion sizes are the most consistent as possible. The variance is as low as possible. And then you see here that the way we usually cut onions is vertically. Then there are some people that don't care too much about their fingers, that this radial cuts. And then you can argue that the best cutting angle is this angle here, because this corresponds to the smallest variance in the onion size per cutting angle, per number of cuts. Just something fun. Okay, so now we get to boosting. So the question is that can we address again the shortcomings of a single decision tree being weak in some other way? For example, rather than performing variance reduction on a complex tree, can we decrease the bias of a single tree so that we can make the tree more expressive? And this comes to the following question, which is, can we learn from our mistake? One way of solving this problem in order to make a model more expressive is another class of ensemble method, which is called boosting. Very good. What is boosting? So the key intuition behind boosting is that one can take an ensemble of models, let's call them TH, because we take trees in this case, but it can be any model, and you combine them additively, and then you obtain a single more complex predictor. Okay. Then each model might be a poor fit for the data, but what we can also do is to take a linear combination of the trees. Okay, so that from the linear combination we can get some degrees of freedom, and this will gain some expressibility and some flexibility. And the question becomes, which model should we include in the example, and how should we choose the coefficients or the weights in the linear combination to be? Okay, very good. So we go back to the idea of ensemble methods, and we say, well, don't be dumb. Don't take all the weights and models at the same weight. Try to add a weight coefficient that you can optimize in some way, so that you have some degrees of freedom, and this will give you an idea of how expressive the different trees are. Very good. So gradient boosting is a method of iteratively building complex regression models by adding simple models. Each new simple model is added to the ensemble to compensate for the weakness of the current ensemble. Okay, so this idea of compensation of the mistakes will grow, will come more and more into focus in the next slides. Okay. Okay, so let's do this slowly so that you can appreciate the concept as it emerges. So we start from a first tree. Okay, so there is an idea of sequentiality. So the first tree takes the input data and produces a prediction. Now the following trick is as follows. We compute the residuals, because of course from the residual we know the prediction error. And then this next model is not going to take the original data, but it's going to take the residual from the previous model. Okay. So instead of the models being synchronous, right, instead of the model being averaged, now the models are sequential, right? So now we are trying to use each model to predict the next model. So the next model is going to try to correct these residuals. Very good. So now we have a new tree, which we call T1. And when you think about the problem the first time, right, your first intuition is that you will just sum the previous prediction to the current residual, and then try to correct the residual as much as possible, so that then you're going to have a second set of residuals, and the second set of residuals will be a correction of the first residual by this first tree, so that you can build another model, let's say a T2, which corrects the residuals. And this will be your first intuition. What smart people figured out is that you do not try to correct the whole residual. You just use a certain lambda coefficient, as you do when you do stochastic gradient descent. And instead of correcting the full residual at one go with the first tree, you just correct a portion of this residual. And this portion is controlled by this variable lambda. So in order to repeat the process multiple times, this is going to produce a second set of residuals, call them R2, and then you repeat this operation for as many times as you want, and then you're going to have a collection of trees, let's say n trees, for which you have n successive correction of the residuals, and each of the residuals is corrected, each of the model is aggregated with the coefficient lambda, and we call this lambda a learning rate. Why? Because in the next slide, we're going to see the logic of choosing this parameter lambda and how this relates to the gradient descent. Very good. Here, let's see an illustration of this. So this is the original data. Then we have a first weak model. Okay, so let's say that we take a simple tree which has only two leaves, so just two decision regions. We try to fit this very complex parameter. So the first tree goes up to here, right? And then the decision region changes, and it's a dumb model, but we said that our objective was to use many dumb models. We compute the residual, and now we see that this residual of this red line, and then we build the second model that corrects this residual. So now if we do this best fitting, then the best fitting is going to be another simple model with only one decision one level, and this is going to create a new residuals and new residuals. I correct this residual, I correct the new residual, I correct the residual, and then when I pull everything together, I obtain a very strong predictor, which is a linear combination of the previous predictors. Very good. So now, why does this work? Wouldn't we be better off if we just correct the full residual, right? Why do we need this tuning parameter lambda? In your mind, I think you understand it, right? That since the models are weak, if you try to correct the full residual, then you're going to end up accumulating the weaknesses of the models. And the weaknesses of the models are going to be such that the error that I make on the residual is just as strong as the error that I made with the first, with the previous pass, so that the residuals are not decreasing, in a sense, right? So that trying to be conservative with this parameter lambda means that you understand that the correction has to be done over multiple steps, okay? This is the type of intuition that we have. But of course, if we want to see this, the best thing to do for us is to just investigate the effect of different lambda on the model. And then we're going to see if we can observe this descent in the magnitude of the errors. And then once we understand how this is related to gradient descent, then it will be clear to us why we call it gradient boosting instead of some other more creative name where we don't try to talk. We don't always talk about gradients and stochastic descent, because it's been a long-running theme. Okay. So just let's embrace now some of the functional optimization vocabulary. So let's say that we are trying to optimize a function and we want to minimize. Okay. So when you talk about the optimization theory, we just talk about minimization. That's because minimization is the dual of maximization, and you just want to consider two classes of problem when you can reduce the two classes of problem to one class of problem. So we always do minimization. And when we want to do this, usually we need to compute a partial derivative with respect with some of the variables. And yeah, when you compute this one here, you can find a common root. There is a point in which all the partial derivatives are vanishing, and we call this point a stationary point. Okay, then if the objective function is the property of being convex, then the stationary point is precisely the minimum. Okay, you remember this from your, I think, from your high school days, right? When you have a single variable, then you only have one derivative, so the size of the derivative is 1, so that when if you find the derivative is 0, you either have a minimum, a maximum, or an inflection point. But of course, when you go to higher orders, it's possible that you have that the derivative is 0 in one variable, but it's still decreasing or increasing in some other variable that are different from this one. So let's just review a little bit what is gradient descent for us. So somebody gives us a function. We know that we can compute the first derivative of this function, and we want to find the approximation of the minimum by computing this derivative a number of times, which is allotted by us by the complexity that we have available for our computation. So we choose a random initial point, which we call an initialization point. Then we take a derivative with each of the variables, which are our optimization variables, and then we update the current estimation variable in as the current estimate minus lambda, our learning parameter, multiplied by the descending direction of the gradient, so minus nabla. And the idea is that if the function is convex, then this iterative method will get close enough to the minimum. And in particular, if you have an infinite amount of computation, then you can get infinitely close to the minimum of the function. And this works because the gradient is always pointing in the direction of the gradient of the greatest descent of the function. So if you follow the gradient, we are going in this descending direction. So you are approaching the minimum. If the function is convex, means that there exists only one nice minimum, one nice smooth minimum, and let's say all the paths that we can take following the descending direction of the gradient will take us to this minimum. Of course, we can spend another semester or maybe more on discussing this optimization, right? You understand that in general, this will work even if the function is not exactly convex. If we have multiple minima, we could say that gradient descent will take us to one of the minima. We can say that if we have multiple starting points, we could eliminate the minimum, the existence of the minimum. Also, the requirement for the function to be the derivative could be weakened. As we said, sometimes we are just happy to have a supporting hyperplane to the function. We don't need to be able to compute the exact derivative, but these are things that we touch upon since you guys have a long life, have a long professional life in front of you and academic life in front of you, so you can learn a lot of these things by yourselves. But the idea is that why do we only take lambda steps instead of taking a full step? Right? If we had the choice, right? Why wouldn't we take lambda to be very large, so that when we take a step, we get closer to the minimum of the function, and we don't have to repeat the same iteration multiple times, right? What is the point of taking a learning rate which is not, let's say, infinity, right? So we know that we are descending along this trajectory, right, on these pink dots. Then let's just take lambda larger so that we get closer faster. And the idea is, of course, that if you take lambda too large, then you start jumping between two different sides of the function, and then you might be actually stuck far away from the mean. Okay. Then let's just do a little bit of more discussion on this. So let's say that the function that we're trying to minimize is an MSE. So MSE is quadratic. So this is convex for sure. So when we take the derivative of the MSE in this variable, we see this distance term that appear. And then what we can do is that we can update the gradient descent with these differences. And these differences are exactly the residual. And this is why we choose the model minus the residuals. Okay. So in general, the minimizing the MSE with respect to the lambda hat is not interesting. That's because we know that the minimum MSE will always occur at lambda hat equal to lambda for every n. And learning the sequence of prediction does not produce a model. Okay. So the prediction of the sequence do not depend on the predictor. So what we want to do instead is that the solution is to change the update step in the gradient descent. Instead of using the gradient, we can use an approximation of the gradient that depends on the predictors. Okay, so we can have lambda hat is equal to lambda hat n plus lambda residual step n estimated as a function of xn. So in the gradient boosting, we're using a simple model to approximate the residual at each iteration, right? And the model that we use is exactly that. So gradient boosting, if you see it from a SGD perspective, it's a form of gradient descent with the MSE as a loss function. But what you're doing is that you're predicting the residual with a tree. So and then in effect, right, this is a gradient. It's descending in the space of model as a function sorry. Gradient boosting is descending in a space of models or of function that relate xn to yn. Okay, very good. So why do we want that? Why do we want to relate gradient boosting to gradient descent? Can we just take one regardless of the other? And the idea is that if we can, it can help us import a massive amount of techniques that people have developed for gradient descent in order to analyze gradient boosting. For example, this can help us in choosing the learning rate lambda. As we said, we already saw that the way which we want to choose the learning rate is in order to avoid being bounded away from the optimal solution by the choice of a large learning rate. Okay. When do we terminate gradient descent? So we can limit the number of iterations as we do in gradient descent. So we can choose the number of models which correspond to the available complexity to us. But for an arbitrary choice of number of iteration, we cannot guarantee that we are supposed we are close to the minimum. What we usually do is instead is to look at the magnitude of the residuals and say, well, if the residuals have a magnitude which is below a certain epsilon, then I can focus on just obtaining a certain size of the residual instead of choosing a certain number of maximum iterations. Of course, you guys know that usually you use both conditions, right? You have a certain bound on the total maximum of you have a bound on the largest number of iterations, as well as a bound on the maximum error, and you just stop whenever one of the two is met. And both problems have to do with the magnitude of the learning rate lambda. Okay? So if the lambda is very small, then you see that you're proceeding very slowly. So you're going straight for the minimum, but it's taking you half the eternity. Or you can choose the lambda to be very large. In the case, you keep bouncing back and forth of the function, and you are bounded away because you have a step so large so that your updates will always keep you bounded away from your minimum. And so when we do gradient descent and we go past the basics, is that we have to choose the learning rate to be variable. And so, for example, we can choose the learning rate to be to have a magnitude which is related to the magnitude of the gradients, for however you want to compute the gradients. And the idea is that if we do this, then when we are far away from the optimum, then the gradient should be very large because we have we are in a very steep part of the function, right? So if you imagine the function to be some sort of ball shaped, right? At the size of the ball, you have the largest magnitude, and then when you close to the minimum, then the gradient started becoming small. So that choosing the learning rate in this one manner allows you to move fast on the size of the ball and then slow down as you get closer to the minimum. Of course, if we move away from this very simple convex function, this policy is not always true, right? You could be in a very flat region of your function and be still very far away from your minimum. You guys know that. You know, these rules are just for you to give an intuition. Of course, you always have to use your understanding of the problem and your understanding of these techniques. And yeah, that's it for now. So we move to the next set of slides, which is again on boosting. Very good. I flick to the slides, so I'm sure that they are not corrupt. Okay, so we're here. So we're talking about boosting. Okay, so a couple of slides here on Kaggle. Let's just so have you guys ever participated to a Kaggle competition? Let's do some interaction. Have you ever participated to a Kaggle competition? Usually some classes ask to participate to a competition. Sometimes students do it by themselves. Yeah. Do you know who owns Kaggle? Kaggle is owned by Google. And they have a few $1 million now as a budget for competition. So they're pretty big. And it's a good thing to it's a good way to gain points for gain entries for your CV. And you know, the wisdom of the crowd is that random forest, they're always performing very well in Kaggle because if you combine this random forest with some algorithms for this boosting, then you can do well in many competitions because the model is very flexible and it adapts well at all sorts of data. Okay, so what is boosting? How does it work? And why is it good? So what is it boosting? So we have a decision tree, and we have the idea that if you have shallow trees, then you have very few leaves. You have a high variance, and so it doesn't train well. And if you have deep trees, then you have low bias, but the variance is very high, and the generalization error is going to be large because you're going to do a lot of overfitting, right? So sorry guys. So the decision tree, they grow, and the variance trade-off, this should be the mean animation here, right? So as the decision tree grows, then you see a plot on the bias variance trade-off as the model complexity. So the idea is that why do we only want one solution? We can, since the trees are so efficient, then we can have multiple trees. We want to use a random forest so that the trees are uncorrelated. So the law of large number kicks in the fastest, and we have a very good reduction of complexity. So the variance reduction is very good because the trees are random, but we can still have a very large generalization error. And when the trees are large, then the speed of the algorithm decreases because these trees have, you can think of it this way, right? So these trees, they have a decision function, right? So they are implemented as if-else function. And in a computer, you can parallelize or you can speed up very simply. We know how to speed up effectively linear algebra operation. This is what the GPUs are made for, right? So they're basically general purpose algorithm to speed up linear operation. But in general, the decision, right, if-else operation are not so easy to speed up. And so this means that when you accumulate many of these decision loops, then they get particularly slow. So the idea is that can we address the shortcomings of the single decision tree by modeling them together. And the idea again is that we want to pile them up so we can correct our mistakes. So as we said, though, option one is to operate them in parallel. And then depending on whether you're doing linear regression or classification across various tasks that you can have, right? So you can use a pooling mechanism, which is either voting or averaging. And you see here nice what is happening, right? So this is your model complexity versus the error. So you can sharpen, right? You can sharpen the trade-off between error and model complexity by using the pooling. Okay, so the option two is that you can increase the degree of the node, and the bias goes to 0, and this corresponds to shrinking. But then there came this new idea, which is to try to pull together multiple weak learners in order to produce a strong learner. And the first implementation was this ADA boost, which was invented in '96. Right? So boosting algorithms are fast, easy to compute, and they are very accurate. And there are 3 optimization algorithms. Okay? So let's say that we are doing the finals. This option is okay. So let's go through this. Let's go through this set of slides. So let's say that you have to take in the finals, even if we don't do finals. So there is a certain passing grade. So what you can do is that you can go to a library and get the previous year's paper, and then you find the student. As the rule of thumb is to get at least some of the answers right. So you test out the rule, and you see that it works for 60% of the previous exams. So you know that the rule works so. So then you find a TA, and you ask him to give you a rule of thumb, which is to get at least some of the answers right. So you make sure to focus on the ones that you got wrong before, and so that you go back. And from the previous rule in which you made a mistake, you try to correct this one here. And you figure out that that can improve your performance, because now you just focus on the one that you got wrong. And then the third step is to call the professor, and it tells you that the simplest way is to do cross-validation. So you go back and you apply the rule again so that you can correct again another set of wrong tests that you did before. So the final step is to combine all of these rules together, so that if from one rule you get accuracy of 60%, the second one you get 64%, and the third you get 70%, you can use the different methods to correct each other's mistake. Okay, so that then instead of pulling the expert all at some time, just use one expert after the other, trying to always refine your correct answer. So your final strategy will be to combine the different rules with different weights, and this will result in a very strong performer that will win you an A+ in your score. Now let's see more of this in mathematical terms. And this is the set of slides that we saw before. Okay, so this is the set of slides that we saw before. Sorry, guys, I confused. I missed up the slide order. I should have done the mathematical part and then the intuitive part. We did the opposite. Okay, very good. Should we do a little bit more? Or just to be clear, right? So the mathematical part was this way. When we're discussing the way to combine multiple models to obtain a stronger predictor. Okay. And the idea is that each of them will correct the previous one. Okay, very good, guys. Let's do a little bit more. Let's do another set of slides. That should go. Any questions so far? Let me see. Any questions so far? I think you can see ADA boost. Okay. Okay, let's see ADA boost today. ADA boost is here. Okay, so let's focus on ADA boost. So the idea is that we recombine. Wait. Okay. So the idea is that we recombine the prediction of the end of the boosting process to come up with a final model prediction, or do we iteratively recombine the residual to determine the next set of residual? So when we do gradient boosting, this might not be suitable for application. Can we combine bootstrapping and boosting? How do we choose the lambda parameter? And we can see the other issues later. Good. So let's go back to the motivation of ADA boost. Let's say that you use you keep using the language of gradient descent, so that we can keep connecting boosting with regression, which we know will help us bring the things that we learn about gradient descent to this. So the classification error, we typically want to maximize. In classification, we typically want to minimize the classification error, which is this expression here, right? So the probability that y is different from y hat. And as we said, we minimize this like we do in gradient descent, but the error is not differentiable. So our solution, as always, is to put the error function into an exponent. Okay, so then now we have y times y hat. This is basically an OR function, right? And then we sum the exponent of y times y hat. Okay, so now this becomes, and of course we do the mapping from -1 and +1, right? So that correct predictions always give you a 1, then you put in front the minus, so you get e to the -1, and wrong prediction always give you a -1. This become a +1, so that it gives you an exponent of the +1. So all the right prediction becomes e to the -1. All the wrong prediction becomes e to the 1. E to the 1 is greater than e to the -1. We obtain a differentiable function, and then we minimize the loss. This is an alternative to the cross entropy loss for minimizing the classification error, of course. So then we do is that we take the derivative of this, and you see that this is the derivative, and then this is easier to decompose when we fix the Wn to be exponent of e to the y hat times y. And this is because we see that this is where the reweighting is applied. So the y1 remains as the true label, and then you have this w1. And this w1 is our weight, and the weight is small when the prediction is correct, and the weight is large when the prediction is incorrect. Particularly, right, when the weight is e to the -1, then we have a right prediction, and e to the 1, we have a wrong prediction. Now, we apply the updated step. So now we have lambda n and wn types of omega. So just like in gradient boosting, we then approximate the gradient with a simple model T that depends on xn. So now we train an x3, which takes the x, the w1 times y1, because x is your input, right? And you're trying to predict the residuals. These residuals is w1 times y1. And so basically we repeat this, okay? So that when we repeat this step, at each step, we are trying to learn a model that corrects the residual, and it focuses only on the points misclassified by the previous model. So let's do a minor adjustment to the loss function so that we can get the gradient descent. So we choose the initial distribution over the training set, where a point is selected with probability omega equal to 1 over n. The I step, the classifier, tries to minimize the weighted training data, where the omegas, right, they are this randomization from the uniform distribution. And then we update the weights as omega n, which is omega m e to the lambda I yi t I xn divided by z. Z is the normalization constant for taking into account of the sum of the updates. And then we have the update of our model, when we say that our global predictor is updated with the lambda I t I. And when the lambda I is again the learning rate, we choose a step I. Very surprisingly, right? Now we start with the usual plot, where we have the paid and unpaid as a function of credit and income. So the first classifier just split this class along this hyperparameter, along this hyperplane. So we said that this is a simple predictor, so linear predictor over one of the features. Then this give us a sort of updated weights, as we said, and the weights are updated according to the correctness of the predictor. So now we have different weights for the different samples in the dataset. And now when we do repeat the prediction, then we're going to have a different separator, like a different hyperplane separating the points, because now they have received a different weighting. Again, we update the model by combining the old model with the new model. So the old model was this one here were the paid one, and these are the unpaid one. Here we are pooling the decision with the voting rule, and we decided that one paid and one unpaid correspond to an unpaid, basically. Then we update the weights again according to this parameter, to this sampling omega, which we have updated, and then we find another decision tree. We combine the models, and we see that slowly complex decision boundary is emerging. And if we're doing this, you can imagine that we are really interpolating this this boundary, right, that separates the correct from the wrong. And then, yeah, so then we keep accumulating the boosting model. Okay, now it comes to the choosing of the learning rate. So unlike in the case of gradient boosting for regression, we can analytically solve the optimal learning rate for other boost by optimization. So learning rate doesn't need to be adapted using some rule of thumb based on the gradient magnitude. So we are minimizing lambda, right? So we want to find over the parameter lambda what is the minimum of this exponential error. And if we do this, we obtain that the optimal solution depends on this epsilon according to this logarithmic function. And this epsilon corresponds to the number of errors that have been made in the classification at step I. So at step I, we choose the learning rate as being a direct function of the mixed classification at step I. And yeah, so if you use AdaBoost, XGBoost, sorry, you see that there are different variations of this original AdaBoost. There is XGBoost, so this is an efficient boosting. There is LGBM, it's a library which is used for this. And then there is CatBoost, which works for decision trees and also handles categorical features. Remember that we always say that categorical features are harder to handle because the dimensionality, the cross dimensionality for this. Very good. There's some final thoughts. Is it if they increase the number of trees, this can lead to overfitting? Remember that this is the usual trade-off that we have to do, right? So it's possible that if you have a large number of trees, then we try to fit some specific points that are always misclassified. Yeah, and I think this is the end of XGBoost, of AdaBoost, sorry. Okay, very good, guys. So let's stop here for today. We did our job for today. So let me know if you have any questions so far. Otherwise, I'll see you guys next time. So as I said, release the next challenge. I'll try to release the final challenge today. As everything is ready, I just have to give it a cleanup. Remember that I want it to be a little bit heavier, right? So it has a very strong influence on your final grade. So try to do well in your final project. Hopefully, you guys are all going to take different directions, so that then we can really exchange different approaches to this. As I said, I try to make it as the least deep learning heavy as possible, but it's basically impossible. So you'll have to learn some deep learning, no problem. But you guys will all take deep learning with me next time, so next semester. So no problem there. You study ahead for your course. And I think if we should have another class with frontal teaching in a couple of weeks. And in that one there, we're going to do an introduction to deep learning. But it's going to be something very, very simple, some basics that maybe you already saw somewhere else. And yeah, just a motivation for you guys to take my next class. Let me know if you have any questions. Otherwise, I'll mute my microphone and then I'll see you guys next. Okay?
Bye.
Hello, Hasni. Hello. Well, who someone is going to?
No, I say goodbye.
Wait. Oh, okay. I mean, you're still taking the class, right? What do you mean goodbye? Are you going abroad? Are you doing something? No, you're still here, right?
Me?
Yeah. Why you say goodbye? I mean.
No, it says I'm going offline. I'm going to get lunch.
Don't scare me, right? Don't scare me. So
No, the limit time of dropping the class is last Friday.
I mean, but you should say that you will never drop my class regardless, right? I mean, you shouldn't say that.
Yeah, that's tactical retreat.
Very good. Tactical retreat, yes. So somebody's going back to Singapore. So why can you can't you take like an hour for your final presentation? The person that wrote in chat that they have to go back to Singapore. Try to take some time, right? So yeah, if you can find like an hour, if you can find a meeting room, let me know, right? Are you still here? Is it gone?
Yeah. I'll try, I guess. I'm just not so sure because the internship starts right after New Year's for us.
So that's so because we did push as far as possible in order to give people more time. But yeah, I mean, hopefully you can take like an hour during your entire presentation.
I'll see
Or
how.
maybe you try to come with the least as possible. You know, it's
Yeah. I'll try.
where are you gonna do your internship?
AMD.
Go ahead.
Yeah. I'll be interning at AMD.
Okay.
Yeah, under their diagnostics teams. So maybe I'll be making more CPUs for you.
I mean, for me personally, yeah. Yeah, you ship out some GPU. The one that they don't go to OpenAI, right? You've seen the deal
Yeah,
between OpenAI
yeah, I've
and
seen it.
I will not invest. Maybe if they offer you a full-time job at AMD, maybe I tell them you have to think about it, right?
Yeah.
So are you gonna do a lot of ML then, right? If you have to do diagnostic, I guess there is a lot of data processing, a lot of
I'm
data
not sure because I'm actually a computer engineering student. So I think I may do more hardware-based stuff. And I think what I'm doing is, from what I heard, is more similar to embedded programming, which is what I'm interested in as well. Yeah.
Yes. So you took the class because you liked my teaching so much, not because it was related to your topic, correct?
Yeah, for sure. I love it. And it's an interesting way to do classes, if you ask me. Like, you don't get this kind of opportunity often in Singapore, even in Taiwan as well. Yeah.
I mean, we try to do something compelling for students. Most of the times we fail, but sometimes, we succeed. And which university are you from? I guess then.
Nanyang Technological University, NTU.
Yeah. So in the group, how many of you guys came here to Taiwan? It seems there is a few Singaporean in the class.
If I'm not wrong, in this course, the rest of them are from NUS, National University of Singapore. I think 6 or 7 are taking this course, but I'm not that close to them. Yeah.
Why?
I mean, I went out with them, but as in because they do have their own plans usually, and I also have my own plans, so we travel differently.
Very good.
Yep.
Yeah, but let's stay in touch, right? So even if you go there, if you want to discuss some things, because we have some good contacts with A-Star, right? And yeah, if the opportunity comes to something together, let me know. And it's always nice to stay in touch with the students. Usually they end up having better jobs than me, right? Because my salary is very much capped, but you guys can be very successful in life. Okay, thank you so much. We'll see you next time.
Bye-bye.
Okay. Thank you for talking to me. Okay. Ciao, guys. If you have any questions, let me know. Otherwise, I'll go back to work. Ciao, guys.